Hi, everybody. I'm Al Gore. No, wait, no, I'm not. I'm Richard Steenbergen. This is talk about routing table growth with a little Al Gore joke in there. So the first thing that you have to throw out whenever you talk about routing table size is, oh my God, it's up and to the right, we're all going to die. That's usually what happens at these types of presentations. There's a curve, it looks like it's going up, someone declares that it's exponential, sets a date for the death of the internet. So I'm just kidding, I had to get that out of the way right quick. But this is over the last 12 years, it's getting up there. So why does the routing table size really matter? Because everything you announce on the global routing table is heard by every other BGP speaking router on the planet. So every time someone puts an unnecessary route into the routing table, you get larger routing tables, you use more RAM, you use more fib, you consume more CPU. And at one point the concern used to be, well, there's so many routes that people's routers with 128 megs of RAM aren't going to be able to hold the table. And it's not even that issue anymore. It's about when you have networks that are multi-homed or that are peering a lot, you're going to see a lot of paths. And if you've got a network that's at a major exchange point that peers with a lot of people, realize that 90% of the internet is multi-homed at some level. So what you end up seeing is the same paths over and over again. You end up with a router that's taking millions of paths. And then you have an iBGP setup where you've got multiple POPs, and each POP, for example, wants to send traffic out its local transit because it's better to send it locally. And so inside your iBGP core, you're going to have many, many millions of paths if you're sending these all into your iBGP. And it starts to slow down routing table convergence. It starts to impact performance. And even the top of the line routers, even the biggest memory that you can go out and buy right now, there's starting to be issues if you've got a network of any kind of scale and size. It's consuming a lot of memory, it's slowing down convergence, and no matter what type of router you have, there's more potential for BGP churn. If there's 500 routes where there could have been one, that's just 500 more times the opportunity for flapping and dampening and bad things to happen. So here's a graph showing the global routing table size over 240 days for IPv4 and IPv6. The interesting thing that I find is that it's not very smooth. You get these huge spikes up and down. And it's kind of interesting if you go back and look at what some of these spikes were. Like there's this little spike here kind of back in June that was really brief, or if you go back and look at what's the history of this? Why did the routing table go up by 20,000 prefixes? You go back and look at some of the historical BGP data, like that particular one was SBC, the old AS7132 network, leaked their internal deaggregates to 7018, the AT&T network, for a couple hours, and so that hit the global routing table. But you see it goes up and down in spurts, but the general theme is that it's always increasing. So people ask, what's the distribution of these routes? Where are they? It turns out there's one particular category where they seem to group up, and that's /24s. Compared to all the others, it's the vast majority of the prefixes. And you've got to ask, why is that? Why are there so many 24s? Is it because of legacy reasons? Is it because of old classful allocations and swamp space, or is it because people are continuing a current pattern of using 24s? So I wanted to look at what are some of the drivers behind the routing table growth. So there's a bunch of theories behind it. Actually, I forgot to update this. Should say what are the 5 most common. But the theories that I usually hear when people talk about this are, well, there's more networks that are multi-homing, so that's why more routes are showing up in BGP. There's the theory that your slow growth allocations are causing fragmentation. Someone takes a 20, they have to come back for another 20, they have to come back for another 20. And so this causes more and more routes, whereas if you had unlimited IP space, you could give someone the big block that they want the first time around, then they wouldn't have to come back. The other theory is that it's all being done for traffic engineering purposes. I think that's Randy Bush's theory. Everything's done for traffic engineering purposes. There's a theory that there's a lot of networks that are using redistribute. So what you're seeing is not intelligent aggregation. You're just seeing how they're using the prefixes internally in their own network. And then there's my personal favorite theory, which is people are just stupid. So the theory about more networks are multi-homing. Technically it's true. But right now there are only 35,000 active ASNs. So here's a graph showing from 2001 to 2010 the growth of active ASNs in the v4 routing table. And you see there's like two little split lines, but basically just ignore that. One's showing origin ASNs and one's showing there's some ASNs that are transit only but don't originate anything. But the general point here is that the growth is very linear, and there's currently about 10 times more routes than there are ASNs. And if you look at the distribution of the routes by the ASN size, what I did was I looked at the bottom 20. So, for example, number of ASNs that announce one route is around 14,000 of the 35,000. Number that announce 2, 3, 4. So if you take the bottom 20, that is every ASN that announces less than 20 routes, that's 86.5% of the total active ASNs, but less than 33% of the routes in the global table. So the general theory here is that this is a contributing factor, but it's probably not vastly responsible. It's not vastly responsible for the huge number of routes out there. The next theory was that slow growth causes a lot of fragmentation, which is also true. I mean, technically, if not for fragmentation, you would expect to see a 1-to-1 ratio. You would expect to see one route for every ASN, so you would see 35,000 routes. But the key point to remember about fragmentation is it doesn't just occur from your network to the IRR giving you a block, or the RIR. It occurs at every level. So if you have a customer that takes provider space from you, you're going to have to allocate to them in a slow fashion. If they've got customers, they have to allocate to their customers in a slow fashion. And the reality is there's a lot of networks out there that don't manage their growth very well. If you're a large responsible network with your documentation in order and an established pattern of growth, you probably don't have a big issue going to Aaron or whoever and saying, give me a big block, give me another big block, give me another big block. But if you're a small hosting provider who has very poor documentation, there's a lot of people out there that find it a lot easier just to get provider space than to put all the paperwork together for Aaron, justify everything, get increasing size blocks. And what tends to happen with these guys is if they're a customer with someone for a long period of time, they might get a 24, and the next month they might come back and get another 24, and the next month they might come back and get another 24, and it starts to add up quickly. I mean, how many people here have customers that are like, we'd like 20 Class Cs, please? I mean, these are the kind of people that you're talking about. And it doesn't just harm them, it harms us when it goes into the global routing table. So the problem is it's kind of difficult to figure out exactly how much bloat this is. It's not easy to calculate a number, but it's really easy to find examples. So you start flipping through the routing table, and I had no problem within a few minutes finding this example of someone who announced 129 24s, all from their same provider space, and they're broken up in these little chunks that are almost completely unaggregatable. And the theory is that when V4 starts running out, people are going to become more and more desperate for space, and they're going to start resorting to these tactics more. And so the theory being we're going to start seeing a lot more small deaggregates taking up a lot of space. So the next theory is that it's all traffic engineering. And the reality is a lot of it is, especially for inbound heavy networks. So what tends to happen, you've got your cable or your DSL shop, and they might get a /11 at a time, but what happens is they're in 50, 75, 100, 200, 500 markets around, wherever, and they break these up into regions. So they might be putting out like a 19 or a 20 or an 18 or something per region. And what happens is a lot of these guys, sometimes they don't even run their own backbone network, or even if they do, they still want their transit provider to hand it off to them in the right place. So you might get a cable company that has 50 connections to their transit provider and expects them to hand it off as like an OC48 in this town over here, and then in this town over here, and this town over here. And so every time you do that, you get all this deaggregation. It's also kind of difficult to detect from an outsider's point of view if they don't have their own regional ASN, because what happens is if someone's got their primary backbone AS, and then they've got like regional cable market A, B, and C as separate ASNs, it's really easy to say, hey, that's A, B, and C. But if someone's just announcing it as part of a single AS, you have no visibility into what's the next hop. They could be announcing it out this one session here, and this session here, and this session here, and you don't really know that. But it's also difficult to see exactly how much of this is responsible for global routing table bloat. But if you look at the top offenders on the CIDR report, it's responsible for all the big ones. So here's just a snapshot of who are the top offenders. You've got people that show 92% prefix gains from aggregation. So I wanted to kind of look at that and see if I could verify that that was true and that it was really something that they could and should be aggregating, or if it was something else. So for example, I went and looked at Bell South, not to pick on Bell South, but they're just the top one on the list. And I went and found the following aggregates that are, if you look at them, they're all like DSL blocks. And then the number of more specifics that are coming from the same ASN with the same AS path within that aggregate. And they're actually announcing the aggregate too. And in some cases they announce the 12 and the 13 and the 14 and the 15 and the 16, and then they get down to all the 24s. But with just Bell South alone, they could very easily be suppressing 2,800 prefixes just from only announcing the aggregates to external networks. So the next example down the list, Time Warner Telecom, same kind of story. You've got these big blocks where there's these internal de-aggregates that are getting out that maybe they don't need to get out. So this technique, which I thought would be really self-explanatory and easy and everyone would understand it, but I'm continually amazed by the number of times I explain it and people go, oh, that's a good idea, why don't we do that? There's a very easy way to still get your traffic engineering and have your cake too, and that's announce your more specifics with a no advertise community. So what happens is you allow your aggregates to propagate normally to the internet. The aggregates draw the traffic into your provider. This works if you're connected to a single provider or a couple providers or whatever the case may be. You allow your aggregates to get out to them. Once the traffic comes into their network, more specific prefixes take over, start directing the traffic. Hey, I want this to go here. Hey, I want this to go there. It's really as simple as just setting a community on your route. It's not that complicated. And yes, your provider still deals with the increased routes, but what happens is if more and more people do this, you distribute the load across different providers, and so not everyone has to deal with all these routes. And it also has the benefit of reducing BGP churn. So one of the theories is that there's lots of redistribution out there. So to look for redistribution, what I did was look at routes with the unknown BGP origin code, because unless you reset it manually, that's what's going to happen when you do redistribute. And it turns out there's about 9% on the global routing table that has an unknown origin code. And if you look at the prefix distribution, yeah, it's a bit higher than the normal routing table as far as there being a lot of 24. So like the theory would be someone gets a 19 and they use 24, 24, 24, 24, and rather than announce the 19, they just turn on redistribute and all these routes magically go out. So there's some truth to that, but it's not a huge percentage. It's only 9% of the global table. My personal favorite theory, people are just being stupid. So here are some of the worst offenders with people that have large numbers of routes with the exact same BGP attributes, AS path, etc., per 16. So for example, this first one, here's a /16 that has 226 more specifics, all announced by the exact same path of the exact same origin. And the thing that I find interesting is that most of these tend to be outside of the US. I get into more analysis later, but here's proof that there's a lot of people that are doing things that are kind of stupid. So the next question was, is there a way that we can kind of look at this globally and see if we can find a pattern? So what we did was we looked at routes. So basically we walk through the routing table and we take it as 16 at a time. And this, this only focuses on the 24s. As we saw in the aggregate, a lot of times what happens is someone gets a /11 and they announce it as a bunch of /20s or something. And so these don't even show up because there's not a huge number of them per 16. But this is kind of focusing on the lower end. This is focusing on what's the cause of all the 24s and things that are longer than /16. So we look at each /16 on the internet, whether it exists or not, just looking at it as a block, and count the number of routes that have the same origin AS, and then group it by how often does that occur? So if you look, for example, people that announce more than 200 of the same origin AS within a particular 16. And this is number of routes that they're responsible for. So the interesting thing is there's kind of a sweet spot here, and the number is between 50 and 74. And if you actually look at, between 10 and 49, there's a huge drop-off. It's not people that are announcing 30 of these. It's that there's people that are especially announcing between 50 to 75 of these. And the rest kind of contribute, but that one little segment is almost half of the total that's responsible. And there's about 45,000 of these deaggregates. And if you go look through the list and you're like, well, do they really need this? What is this for? I mean, it's really obvious that some of these are just completely unnecessary. So the next question was, is there a specific breakdown of these per country? So obviously the US leads because the US has the most routes. But it's kind of an interesting breakdown in that India is a close second. The one that surprised me, and actually had to make this graph go all the way out to find China. China is not responsible for that many unnecessary deaggregates. So however much spam and DDoS you get, you can thank them that they're not sending out deaggregates. So then the next analysis we did was, what's the percentage of these deaggregates compared to the total routes originated in this particular country? And this comes from, what's the country of the ASN. So yeah, it's not perfect if you've got a global ASN, but most of these things are pretty regional. So it turns out that India, having almost 8,000, having around 7,500 or something of these unnecessary deaggregates, that's 50% of the routes that they announce. And it's really obvious. If you go look, there's a certain handful of ISPs that are really blatantly bad about announcing everything as 24s, 23s, all kinds of crazy stuff like that. There's certain other countries that are extremely high in the same regard. The US is actually pretty low. But these other countries, the total number has started to come down. So India is the really big one where the total number is still high, and it's a huge percentage of the routes. So I went and looked at what are some random funny bad blocks, and I noticed that Starbucks actually has a /14 that they use for all the wireless and all the different Starbucks, and 7018 is actually originating them all as 24s in these little chunks. But the problem here is it might actually not be 7018. It might be someone announcing it with a private ASN because those are going to get stripped by the time they make it to the global routing table. So this illustrates, you're not sure who to contact. You're not sure if this is AT&T's fault or if this is their customer's fault. I mean, you could contact AT&T directly and ask them, but you're not always guaranteed to know who's responsible. There could be a private ASN in there somewhere. So the next question is, what's the impact of IPv6 on the routing table? What is this going to accomplish? So here's a comparison of routes versus ASNs, and the top graph is v4, and you can see on the bottom there's been a very slow growth of ASNs, and the prefixes are kind of outpacing that until we're at the point where we're at right now, where it's 10 prefixes for every ASN. If you look at IPv6, it's much closer to 1-to-1. It started out really close to 1-to-1, and it's kind of been diverging over the last couple of years. But the general theory is that we're much better off in IPv6. So, because the blocks are larger, the theory is people only need to take one block, hopefully for the rest of their life. And if not, then maybe they need a bigger block. But there's going to be a lot less prefixes on the routing table. And I think a lot of people are still kind of stuck in this notion of every time they think about, well, what kind of reallocation do I give a customer, they think, well, what's the most efficient use of space? And that's not the reality anymore. In IPv6, the question is, what's the most efficient use of the routing table? And so, people need to stop and think about that. Do I really need to be restrictive in my space, or should I be giving this person enough that they can grow and cover all their needs? And the final question that we had was what's the relative growth? So the theory that I talked about earlier on was, are 24s running away? Are they rapidly increasing as a particular subset compared to the rest of the routing table? And the answer is right now they're not. They're actually in the middle there somewhere, and there's much larger blocks are having larger increases. But at the same time, over the past 240 days, there's been about a 7% increase in 24s. So it's still a huge number, but percentage-wise, maybe we're not seeing that yet. And obviously, we haven't run out of V4 space, so maybe when that happens, we'll start seeing a really large runaway of that. But that's basically it. Questions?
Oh,
hello.
It's almost a tie. We'll take gentleman in the back.
Jeff Houston,
Jeff,
hey, Nick. I've got a couple of questions, Richard. Let me start with the first one. I think it was about slide 2 or 3. You said more BGP routes means more BGP churn. That's it.
Yep.
Have you measured that?
Nope, that's just a general.
Okay, I have, and it doesn't. Weirdly, the amount of BGP updates you get, if you get rid of the sort of the local session resets, and you look at the stuff that comes from everywhere as background BGP noise, oddly enough, it has nothing to do with table size. In fact, it's been constant for about 3 years.
Is it about 2.3 Kelvin?
It is indeed like 2.3 Kelvin. The real answer is 3.48. The amount of BGP noise is actually directly related to the average AS path length. You're actually looking at the protocol, not the network behavior. So that last point, why is this a problem? If the problem is, oh my God, BGP is going to become less stable as we get more routes, the data that we have so far doesn't say anything about that. In fact, it says the opposite. My second question was, you talk about the amount of BGP entries growing as a bad thing. Why is it bad?
Okay, so first question, you're right, I didn't actually measure it. It's just a general assumption that the more routes there are, the more potential there's going to be for churn. But obviously, as the protocol goes, you can announce multiple NLRIs for the same attributes. So if it's just someone flaps their link, it doesn't matter. But if it's people adding 24s or moving 24s, that kind of thing, maybe that's not instantaneous. Maybe that's not a flap. Maybe that's just general churn. But are we seeing 24s being higher than they were before? We're not. So maybe that's the answer to the question is we haven't seen a particular subset of routes grow versus others.
So if the metric we're looking for is something like if it grew at the rate of Moore's law, we should all get worried, yeah?
Yeah.
So for the last 5 years, it's been so low compared to Moore's law, we can all go back to sleep. The amount of entries in the IPv4 routing table is actually growing relatively slowly, despite all this massive deaggregation. And what I get round to sort of thinking about is, are we accustomed to saying to ourselves, BGP is out of control, versus looking at the metrics of BGP and actually looking at what's the unit cost of routing, and is that changing over time?
So my particular motivation for this was actually that we are seeing problems in the production network because of large numbers of routes. So there's 2 problems that we're seeing. Number one is when I talk about having a large number of paths, we've actually seen this problem especially on Juniper. But what's happened is, and this has gotten worse over the years as kind of the code has bloated, but there's a certain point where when you have a certain number of paths and Junipers try to exchange messages over BGP, the act of actually transmitting or receiving the BGP message will actually block the installation of the route into the fib. And many other people have seen this kind of ongoing issue where it can take 20 minutes to exchange, to install any routes into the fib after you restart the router, because the boxes are so busy with BGP I/O. And this is obviously a vendor-specific implementation issue, but we're really seeing that as a big problem. Every time we reboot a router, we've got core boxes that have core iBGP views where, despite our best efforts, and we can't run advertise external and improve convergence time because that increases the prefix load. We can't run add paths because that increases the prefix load. So even looking at the best case optimal solution, we've got these routers with 5 or 6 million paths. and it breaks convergence. We're actually seeing it break NSR, nonstop routing, where it literally takes so long for the routing engines to sync to each other that they can't complete an in-service upgrade hitlessly. The other issue that we saw is there's another vendor who I'm not going to name specifically who rolled out a major product that a lot of people are using that has this particular issue where they split the routing table across 2 memory blocks, and the way that they do this very naively is put /0 through 16 in one and 17 through 32 in the other, and obviously that doesn't work, and that's a very big problem as well. So yeah, I mean we're seeing these issues in the network.
Right, just as a final comment, I've also measured the average time to converge. And over the last 5 years, it's been constant at about 72 seconds. So some parts of BGP have actually been remarkably constant in the face of remarkable growth in the table size.
I'd like to
So
show you my network then.
BGP, doesn't scale up in the same dimensions all the way.
Well, it's a problem for us.
Single prefix.
The average time for a single prefix to converge.
Patrick?
Okay, Patrick
That
up
was
front.
the average time for a single prefix to converge.
Okay.
Yeah, he's saying.
Yeah.
He's saying hello, I'm Patrick from Akamai. I did watch the talk, I really did, and you gave 5 things and you went through them, but I'm not sure which one you think is actually the problem.
My personal theory is that the majority of it is stupidity.
Yes, but that's true for everything.
It's not a new insight, but
Just checking.
Chris.
Oh, sorry. Chris Morrow, Google. So I like the presentation, the part that I saw. I apologize, I missed some of it and had to listen from outside. But I have a couple questions. It seems to me that the growth of more subnets from a larger prefix, and either people don't announce the covering prefix, which I didn't see you remark if that was the case in all of these cases or the majority of these cases.
The large ones, like the top 5, that's all the case, and then once you start getting lower, that becomes less the case.
Okay. So there's some education, right, that could be done and said, hey, by the way, you can break this up if you like. Somebody upstream is probably going to filter them. And I'll use the wrong name here, but I think John Lewis from Atlantic provided some template material for 6500 configs for slapping down prefixes that were already covered, right? Mm-hmm. So that sort of work would be useful to see as sort of a best common practice and something that might be useful, right, to you. But so there's some education. Please make sure you send your covering prefix out. If you don't, then you're going to lose reachability potentially. There's also the reasoning behind it may be that they have a set of paths that are congested, and so they're trying to traffic engineer across those. And so Jason Schiller actually has a great presentation about this particular thing with a Caribbean ISP problem.
That may be true. One thing that we noticed is that once you start to get into like the really small ISPs, like some random like really small DSL provider in Russia, they actually do like there's varying prepins on these 24s, and they're trying to move them in different ways. And like maybe that's not your best traffic engineering technique, but from looking from multiple sources, they're the same AS path. Sometimes they really do. They announce them to different providers, and sometimes they're just varying the AS path. But yeah, that's definitely out there.
Yeah. So I wrote a whole bunch of notes actually, but so it would be nice to see like the V6 curve actually slid back to the left against the V4 curve and see where at about the same time period for deployment, what does that look like?
Yeah,
is it sort of the same? Because it's a very stark difference today, but V4 has had 20 years to bake, and V6, even though it's had 15 years to bake, has actually been deployed for like maybe 5, right, in a sort of semi-production sense. And I think the issue of is it stupidity or is it other things, some of it I think is that there are very few tools that exist for the average BGP engineer, right, if there is such a thing. But they basically say, well, I need this prefix to be seen over there, let me make the longer version of it show up over there, right? As opposed to let me twiddle meds or use the provider's community tools or what have you. So either some protocol work to figure out a better answer to this, right? Or some educational work to say, here's some things to do. And there are things that vendors have produced like OER from Cisco that kind of toss a big wrench in all of this anyway, because they de-aggregate for you. To some extent.
Yeah,
anyway,
I think everyone's kind of responsible. Everyone's does a little bit of this, and I look through some of my announcements, and I'm kind of guilty too. There's things where we had to allocate a block out of a particular region that wasn't the correct region, so we had to announce it over here to make it route right. Everyone's responsible, but at the same time, when was the last time most of you went and looked at your announcements and said, are we doing this efficiently, or should we be improving this? And the other thing is, when have you gone to your transit provider who is responsible for some of this and said, we're not going to buy from you until you clean up your act?
Just 1 second, folks. We're going to close the mics after Jared because we're starting to run a little bit tight here.
Jared Mach, NTT America. So I was wondering if you had actually reached out to any of the service providers, or you called out Bell South as well as Starbucks there. I'm wondering if you'd reached out to any of those people and tried to figure out why they're doing what they're doing and actually get in their head and try and educate them. I've had some limited success with doing this myself in the past, but there's only me sending out some of these emails to people complaining about people's routing announcements. And I think if we gang up as a community, maybe we can make some progress, like have a routing announcement of the week that we're going to target on the NANOG list, and see if we can actually pressure some of these providers into improving their behavior.
Yeah,
have you tried to talk to anyone about that?
Not this time. I did several years ago, and I didn't have much success. Like, a lot of these people are just kind of running on autopilot. I didn't this time because I kind of wrote this presentation like 3 days ago. You know, there is the CIDR report, and I think people have kind of tuned it out at this point. Like, no one looks at it to say, oh, Bell South's still on top. Nope, it's still on top.
Yeah, maybe we should collaborate as a community and actually do something productive as far as this goes. Yep. Hopefully we can maybe recruit some volunteers.
And I would think at some point shame would come into it. Like, you know, these networks have got to be motivated by, oh, we look kind of bad, maybe we should clean this up. And it's not that difficult to clean up in most of these cases. It's some effort, and right now there's no reason for them to spend any of that effort at all.
Yeah, I think people being a combination of lazy as well as ill-educated in this space is probably 99% of what we're actually observing here.
Yep.
Thank you very much, Russ. And if I can please call